Hey guys, this will be our first video for chapter number 14, which is all about solutions. Solutions are when we take a solvent and we dissolve a solute into that solvent. To start off with, we're going to have a lot of vocabulary, so we're going to start with just a minute and a half of Professor Dave Explains, where he's just going to rattle through a bunch of vocab terms, and then we're going to come back down and I'll write them down along with a little bit more explanation of each of them, along with, kind of a functional definition for our class. So, with no further ado, let's see Professor Dave explain.
A homogeneous mixture that's in one phase is called a solution. Think of something like table salt in water. If we are talking about a liquid solution, the thing that gets dissolved is called the solute. In this case, that's the salt. And the thing doing the dissolving is called the solvent. Here, that's the water. Solutions tend to retain the properties of the solvent, since solvent particles are typically much more abundant than the solute. We can say that a solute is either soluble or insoluble in a particular solvent, depending on whether it will dissolve in that solvent. Something will dissolve if in doing so it will make favorable intermolecular contacts with solvent particles. In the case of salt, it will dissolve and dissociate so that the sodium ions and chloride ions can make ion-dipole interactions with water molecules. A nonpolar covalent compound will not dissolve in water because without a dipole, it can't make any dipole-dipole interactions with polar water molecules. That's where we get the saying, like dissolves like. Salt water is a strong electrolyte because the formally charged ions in solution can conduct electricity. Weak electrolytes only partially ionize in solution, so they conduct electricity weakly. We can use molecular equations to describe substances.
Okay, and that's where we're going to stop. This molecular and ionic equation stuff is great. He even goes over a little bit of a review of the reaction types after that. So you can obviously right here see the name of the video. If you want to come and watch the entire thing, you're certainly entitled to. But for this chapter, for chapter number 14, just that first minute and a half really is relevant for us. So let's get switched back over here. And now we're going to take a look at kind of what are some of these terms that he just rattled through, and can we provide a functional definition of them? So we better start off with what we're talking about in this chapter, which is what is a solution. Now, Professor Dave said that's a homogeneous mixture. And just to refresh your memories on what a homogeneous mixture is, a homogeneous mixture is anything that's composed of two or more parts that are not chemically combined. So they're physically mixed up together, but they haven't chemically bonded. And they're evenly distributed so that you can't look at one section and see anything different than anywhere else. It's all even everywhere you look. That would be a homogeneous mixture or a solution. The two terms are interchangeable. The other thing with the solution that probably should be mentioned at this point is it can be made out of any state of matter. A solution can be two solids mixed together, like in the example of steel. Steel is a mixture of carbon and iron. The carbon and the iron don't actually chemically bond, but that presence of the carbon in the iron gives it some different properties that we then call it steel. Any metal alloy is the same. The metal alloys are all mixtures. The air around me is a mixture of gas in gas. Nitrogen being the larger gas that's dissolving the other ones, oxygen, argon, carbon dioxide, and then the other trace gases down below carbon dioxide. We can have mixtures of a gas and a liquid, like the oxygen being dissolved in water that allows fish to breathe. Fish do not break the oxygen out of water, the H2O. That O in the H2O is chemically bonded to the hydrogens, and the fish do not have access to it. Instead, what they do is they filter out oxygen that's been dissolved by the water. And so, again, solutions can be any phase of matter. Okay. The next thing we want to do is kind of talk about these items that are dissolving or being dissolved in scientific terms. And so those terms are solute and solvent. The solute is the thing being dissolved. And I apologize for that email ding. I've got to learn to turn off those notifications when I make these videos. That was my computer, not yours. And the solvent is the thing that's doing the dissolving. So if we were to take some salt and throw it in some water to make some salt water, for example, the salt would be the solute. It would be the thing that's being dissolved, and the water would be the solvent, the thing doing the dissolving. And the solvent is usually present in larger quantities. So if you have to take a guess, if you had two chemicals that you mixed together and you made a solution out of them, they made this homogeneous mixture when you mixed them together, and that they didn't chemically react, so that you would have a solution of some type, you would consider typically the solvent to be whatever you had more of when you threw it all together. Okay. Now, some things, as Professor Dave said, some things can be dissolved by some solvents, and some things can't be dissolved by some solvents. And that gets to this idea first of whether or not something can be dissolved. If it can be dissolved by a particular solvent, can be dissolved, then it would be soluble in that solvent. So like salt. Salt can be dissolved by water, so we would say salt is soluble in water. If it cannot be dissolved by a particular solvent, it would be said to be insoluble. Now, if they don't attach anything else, if someone is to mention these words soluble and insoluble and they don't say what solvent, then you can assume that that solvent is water, but these really are conditional because, again, certain substances will dissolve in certain other substances and not in others. So these can be understood to be insoluble or soluble in water if a solvent isn't mentioned, but a solvent really should be mentioned. Can't be dissolved by a particular solvent. Okay. And the reason for that, why some things can be dissolved by others, is this phrase, like dissolves like. I guess this isn't the reason, but it's a good way to remember it. And now, in last chapter, we talked about these intermolecular forces a little bit, these different ways that molecules can attach to each other. And one of the things that we found out is that polarity of a molecule really matters a lot. Whether that molecule has positive and negative regions to it or not really has a large influence on the chemical properties of that substance. So something like water with this bent molecular geometry. So water's got kind of this, the hydrogens there and the oxygens there, and it makes this kind of V shape. And remember that it's polar, so the strongly electronegative oxygen is kind of hogging the electrons, and these weakly negative, electronegative hydrogens are kind of less strongly pulling on those electrons, and so it gets this positive and negative region. And those positive and negative regions allow it to attach to other things that are positive or negative. And so we can call those, dipole ion interactions. If this other thing is an ion, like a sodium, that would be attaching to that oxygen. Or we can call them dipole-dipole interactions if it's like this oxygen from, say, another water molecule being attracted to that hydrogen. And in fact, this particular type of dipole-dipole interaction has a special name. It's hydrogen bonding, because it's this kind of strong dipole-dipole interaction. Again, that's with oxygen, nitrogen, fluorine combined with oxygen make those kind of hydrogen bonds, or combined with hydrogen, make those kind of bonds. But this kind of is the reason, or explains why, like can dissolve like. If I've got some positive and negative regions here, I can interact with the positive regions of the Na, or if we had sodium chloride, the negative chlorine. And so we can get some attractions forming there. These molecules can attach, and we can dissolve. But if I had something that didn't have that polarity to it, it didn't have these positive and negative regions, then water really wouldn't have a way to affect it. And so water, being a polar molecule, can dissolve other polar molecules, and it can dissolve ions. Ionic compounds. Now, if we want to dissolve things that aren't polar, then we need a different kind of solvent. We need, if we're going to engage in a molecule that mainly experiences, London dispersion forces, van der Waals forces, then we need a solvent that mainly experiences van der Waals forces. So something that is nonpolar. So nonpolar solvents dissolve nonpolar compounds. And some of you might be familiar with that, although you probably shouldn't be. You might be familiar with that if you or one of your relatives has ever gotten some grease on yourself and used something like kerosene or gasoline to get that grease off. So obviously, if you get some grease on yourself, water doesn't do a very good job of taking that off. Some soaps can. Soaps are kind of a special class of molecule that is polar in one spot and non-polar in another, and so it allows those two things to attach. But what really does a good job of getting grease off your hands is like kerosene or gasoline, because that's a non-polar solvent and it can dissolve the grease. The problem, and don't please use gasoline or kerosene as a solvent on your hands, because it's carcinogenic. Both of them are, so they're cancer causing, and it would really not be a good idea to use them as a cleaner. Although old school guys tended to do that quite a bit. We know better now. Okay, and one last definition before we're going to wrap this video, and that is electrolytes. Electrolytes are things that conduct electricity. Oops, and I shouldn't put electrons. I'll write electricity because it doesn't necessarily have to be electrons when dissolved in water. And these electrolytes Well, first they have to be things that can be dissolved by water, so they can only possibly be ionic compounds or polar molecules. And then, in order for us to conduct electricity, we need the charges to be able to separate. And basically, what electricity is the movement of charge. And so, if we can take a positive charge and move it one way, while we take a negative charge and move it the other way, well, then we can have electricity being conducted. But if we have polar molecules, the positive and negative charges are attached to each other, like water. We can't, make the hydrogen move one way with its hydrogen or with its positive charge, and the oxygen move another with its negative charge. They have to move together. So polar molecules are not able, typically, to be electrolytes. There are some exceptions to that, especially with the very small ones. But what's much more likely to be an electrolyte is an ionic compound. Because when an ionic compound dissolves, the positive and the negative portions of that compound can travel freely from each other. And so they're able to carry that charge to different places, which is that movement of charge is what we know as electricity. Okay, so here we had a whole bunch of terminology, just the vocab stuff to kind of lay the groundwork down. Our next video is going to be much more mathematical. One of the things we need to be able to do with these solutions is to measure how strong the solutions are. And unfortunately for you as a student of chemistry, there are a number of different ways to measure the strengths of solutions that are used actively in a number of different industries. And so we're going to introduce you to, well, if not all of them, at least a good majority. So typically pretty easy math coming up, but a lot of different little bits, just each calculation's easy, but there's a whole bunch of different calculations. So, but anyway, that's next video, not this one. So I hope you all are enjoying yourselves on this fine spring day, and I will see you in the next video.